Hi, my name is Clark Gellings. I'm a fellow with the Electric Power Research Institute. This is the fourth lecture in a series that relates to demand-side management and demand response, sponsored in part by the University of Minnesota. In this lecture, we're going to focus more on the demand response integration from a communications and power system perspective. Let me start with the idea that in order to have a truly ubiquitous demand response system, we're going to have to be able to communicate with customers' buildings, appliances, and devices, and that kind of starts with the need for standards and open architecture. If you want a great example of harmonized standards, think about the NEMA plug that we use in the United States. It's a harmonized standard, promotes interoperability. We don't have problems in interchanging 120-volt appliances within the United States. And even when we approach another country where they themselves have standards that are harmonized, we can find adapters which will allow compatibility between these devices. Where standards have not been harmonized, open architecture could allow the interoperability through the use of those sorts of adapters. And the same is true in the power system, and the same is true in considering demand-side management. If we thought about the interoperability of data communications within the utility system such that we can extend our reach for communications into buildings and into energy-consuming devices and appliances, this is an illustration of a plug-socket analogy of interoperability for data communications. We would have potentially a transport layer where we have physically transporting and routing data over the network. We could have a network management layer which connects the device language with the network communication, and an application layer where there's a standard language for exchanging information. We are not there yet within the electric utility industry, although we have made great strides in this regard. In fact, in the late 1970s, early 1980s, we got together as an industry and formulated something called the Utility Communications Architecture, or UCA, which led to the development of an International Electrotechnology Commission standard called IEC 61850, which in large measure is now the backbone of what's called the smart grid, this evolving power system which integrates communications, sensors, and computational ability. Now, if we think about taking that smart grid and we want to in turn communicate with appliances and devices in buildings and homes, we've got to allow for the fact that we've got to have a variety of transport mechanisms. Some will be wireless, some may be fiber optic or not, or some may be wired, and there may be other routes as well that I don't even see yet. But to do this right, we've got to have a common language that's vendor neutral, so that we're not designing a system based just on one vendor's system, so that we don't have utilities and consumers stuck with the beta VHS kind of controversy that we once had. The result of doing this effectively would allow us to integrate systems within the utility that determine and predict prices with systems in customers' buildings. Here's an example of one of these early demonstrations of making this work at the world's largest hotel, the Marriott Marquis Hotel in New York City. The 1995 study that was done, basically we integrated into the building's energy management system the ability to receive and react to pricing signals. And we basically, as the prices rose during the hottest part of the day, we basically sent those signals to the hotel. And here on one day, because of the ability to move some load around, shed some, reorganize some uses, we saved that Marriott Marquis Hotel $6,900. More importantly, we reduced the peak demand on the New York power system at the time. We did it again at the World Financial Center, which was right across the street from the old World Trade Center. Two 30 to 40 story towers with 5 million square feet of office space with some major tenants, including Merrill Lynch and American Express. We had 10 1,500-ton Carrier chillers, air conditioners, and 3 million gallons of thermal energy storage, with 37 major pumps totaling 5,300 horsepower and an air handling system. We were able to manage to reduce their peak demand of 60 megawatts by nearly 10% as a result of having this kind of dynamic system in place. This kind of approach even applies towards household utility shapes. Now here's a disaggregation of a household utility shape. Maybe most of you have never even seen this. It's quite interesting. Here we've plotted the variety of uses. Not surprisingly, the dominant use in this illustration is space cooling and water heating, shown there in pink. But there are some others that are substantial, like clothes washer, dryer, and dishwasher, which, for example, occur at a time of potential system peak, and as you can see, might very well therefore aggravate what it would be the total load shape and its impact on the utility's peak demand. Cooking is in there as well as other uses. And one of the questions that have been asked is what kind of direct end-use switching might be best. And so this set of slides illustrates a couple of levels of home area network control that might be used, where end uses such as central air conditioning, lighting, and ceiling fans were controlled through utility control demand response control strategies by reducing compressor speed, for instance, so not turning it off but reducing it, turning off some lights, not all, reducing speeds on ceiling fans by one level, again not off. The idea there is it's important to leave the customer with some service, some degree of comfort, rather than to completely disable the service to the customer. You get much better cooperation and response to the customer. Here's a second level of what this might look at with some intelligence added. Okay, so this is taking all utility control demand response and all those level 1 strategies and then looking back at the central air conditioner and reduce continuously variable compressor speed to offset the instantaneous draws of washer, dryer, and the like. See how this is becoming dynamic? To control TVs and set-top boxes and the like, to disable those which have a standby draw, the so-called parasitic loads or vampire loads as they're sometimes cut. You're not cutting off TV I'm watching, you're cutting off the set-top boxes and the other things I'm not actually using, which can have a significant demand on the power system. In refrigeration space, I might disable the auto defrost cycle on my refrigerator, and that on the lighting, I might now turn to do some dimming. If you think of the sequential dispatch in both of those examples from one level to another, I might start seeing this kind of change from the baseline demand to enable the amount of demand response that's shown here in red, or in green, or the demand response now shown in pink. Two different levels of demand response within this structure. And the benefit of that, and this is what's important, is that I can see a marginal benefit in the first control category of demand response of somewhere between $190 and $500 a year, whereas in the second level, I might not see nearly that benefit. In fact, I might see an adverse impact. So how I control these end-use appliances and devices is very critical to understanding whether there's really a net benefit to the power system. The next step to this is going to be seamless real-time transaction between consumers and suppliers, so that you're going to take the idea that I expressed here in the Marriott Marquis Hotel, and you're actually going to have a system in the cloud that allows for an aggregation of a number of customers through some kind of grid-connected energy resource interface, and allows this collection of customers to be controlled in a way so as to mitigate the impact of those of demand on the wholesale system, and then carry the benefits back to the collection of customers that's involved. Now, one of the issues we have is how do we implement this stuff? I mean, if I'm going to do this here using a residential example, I'm a utility. I got to roll a truck out to the customer. That's expensive. I've got to go get the customer, make sure he's home. He didn't change his mind. He didn't forget. He lets me in. I'm able to install the hardware. It's physically possible. It's not like it's in a place where I can't get at it. I install the hardware. It could be the relay and the communications device that I mentioned. I might have to connect it to an appliance, or it might be that I wire it in at the service panel. And then I'm left with whether this is reliable, persistent, and dependable. For example, does the customer decide to change his mind and tell me he no longer wants to be part of the program? Not an easy task in any case. So we've done some surveys of utilities and asked which of the following demand response models would your utility prefer for DR-ready appliances? An automated response, where the customer pre-programs the appliance based on preferences, and he has to manually override it. I mean, you go and shut something off. If he doesn't like it, he has the opportunity to override it. Or a behavioral response, where the customer receives a signal and then may choose to take an action. Not surprisingly, automated response turns out to be the preferred from a utility perspective, and actually the most practical in terms of making the programs really pay for themselves. And so we've had a focus in the industry lately on residential appliances and devices to make them DR ready or demand response ready. And the reason for residential is that the appliances are mass produced, they're widely distributed, they offer an enormous diversity. They were targeted in the 2000 Energy Independence and Security Act of the United States as being smart grid appliances, and that gave us some entree to continue some dialogue with federal agencies about making a program work that's automatic demand response, or auto DR. The technical challenges I suggested is developing the standards for exchanging information with smart appliances from the grid through a media agnostic system into intelligent communication gateways and appliances. Some suggestion that we do this directly. We do it through a portal, or we do it through communications, consumer electronics devices, and to develop a standard data packet for two-way communications and data exchange in the process. And we think the path to this DR-ready is either through the DR-ready, developing a set of DR-ready appliances. Think about appliances that have a built-in chip. Every appliance of any size that's made that has a potential large electric demand has a built-in chip. Really cheap to do because we've got the electronics in most of these already. I could also do it through DR-ready information technology and consumer electronic devices, or I could do it the way it's done now through electric utility installed demand response devices, which clearly, as I've pointed out, are expensive. And so there's a couple of options to do this that are being pursued. One is to modify the Energy Star program that we now see labeling many of our appliances and devices in the home, and have them modify their program so that they include the necessity to be DR ready, develop a separate Energy Smart kind of program, or pursue some other kind of market mechanism. The candidate product areas for this DR ready designation, the priority areas, tend to be the obvious larger energy consuming devices that are somewhat ubiquitous in buildings and homes, room air conditioners, central air conditioners, dishwashers, clothes washers, water heaters, pool pumps, refrigerators, freezers, and so on, and electric dryers. With future areas possibly including generation that's on the customer's premise, standby, or even distributed generation. Possibly thermal storage systems that would enhance the overall load profile of a building or appliance or device if I could arrange to control them properly. Even fossil fuel devices, furnaces and boilers, and certainly battery chargers, especially for those powering electric vehicles, even standalone energy storage devices like batteries, which are potentially to be used to manage consumer demand in response to time of use pricing. So, quiz here. The largest impact from reducing demand is from controlling what? Central air conditioning, lighting, fans, refrigerators, TVs. What's the answer? Well, it's central air conditioning. That's the largest potential impact. Um, Second question, DR-ready appliances must include what? Welders, motors, gas water heaters, or most white goods? Well, some might say potentially all of them except for perhaps gas water heaters. But what we're really talking about is most white goods that could be DR-ready appliances. I hope you've enjoyed this series of 4 lectures. I enjoyed doing them. Thank you very much for your time.